Okay, sweet. We're now live. Um, so I said yesterday that I was planning on streaming for 2 hours today, and then probably on Friday for a few hours. And the primary reason for that is in my sessions here, I haven't been able to make really any progress on the exam, and was really only being able to do mostly, Anki, which is not ideal. Um, the reality is like most of these videos were like, or I guess some of these have been quite shorter or quite a bit shorter. And so if I think I stick to my hour length, and then also if I work to try to get through Anki quickly, I think we'll be able to do the things we need to in terms of like making progress on stuff while still being able to review the Anki within an hour time frame. Yes. And then one thing that's like interesting or nice about this approach is that, or I guess about this like approach generally, is that my only contact with calculus occurs during these live streams. So like from end to beginning, if you watch, the calculus self-teaching, that is like these videos will encapsulate everything I've done to learn calculus, and no effort was done outside of it. I guess maybe like sometimes I think about it, right? But no, like actual like sit down, effort. So that's interesting. Yeah. Okay. Okay, so I think we're on 2. I'm gonna grab some water real quick. Okay. Perfect. Okay, so we have A, B, and C. I was able to do the mean value theorem stuff. I don't have a 4, so we're going to go to 2 here. Okay, find the limit if it exists. If it does not exist, explain why. Okay, I can do that. Okay, so so this will be find the limit if it exists. If it doesn't, explain why. Actually, let's zoom in here so we can. That's probably good enough there. Maybe one more there. Okay. Explain why. Okay. Okay. That's more readable. Maybe we'll do even one more here. Oh, that's the highest zoom I can go for Obsidian. Okay. Perfect. So find the limit if it exists. If it doesn't exist, explain why. So I think the first thing we tried to do, like if possible, when finding a limit, is to input the limit into the function. So here we have like the limit to 1, but we see that like as the limit approaches 1, or the denominator as the denominator arbitrarily approaches 0, the result of the function is that it goes to infinity, and that's because 1 or 0.97 minus 1, 0.98 minus 1, right? As we approach 1, the number gets larger and larger, and if we substitute x for 1, it's undefined because the denominator is 0. Okay, and so for this one, the limit does not exist. The limit doesn't exist for this function. If we attempt to substitute, wait. Okay, we'll have to check this, but if we attempt to substitute x for 1, the denominator is 0, which leaves the result undefined. As x gets arbitrarily close to 1, we approach infinity. So I'm not sure if the limit of 1 would be infinity here, or if it's like undefined. So when we say find the limit if it exists, yeah, I'm not sure there. So let's get some feedback. Okay, I'm just gonna delete a couple of these. Move this guy over. Okay, find the limit if it exists. If not, explain why. Oh, that's sad. It did not travel well. Okay, if my answer is wrong, then the reason why it's wrong is because the limit does exist for the function, and it's infinity as we approach on the positive side, and negative infinity as we approach on the, as we approach 1 from the left side, but as we approach 1 from the right side, it's negative infinity. Yeah. So that would be the instance when I believe that's the instance where I'd be wrong for this one. Okay. Um, Interesting. So I'm surprised, or I didn't like this last section here. However, we need to examine the limits from the left. Oh my heavens, I need to zoom in. Okay. However, we need to examine the... okay, all the way to the bottom. Okay. However, we need to examine the limits from the left to the right as x approaches. Like, yeah, this makes sense. Go to positive or negative infinity. Because the left-hand limit and the right-hand limit are not equal, the overall limit does not exist. Could you give me the exact definition for when a limit exists? I wasn't aware of this left-hand, right-hand portion of the definition. Okay. Let's see. The limit exists if and only if for every number that is greater than 0, there exists a number... okay, I don't know these symbols here. Could you provide the definition in bullet points and in regular English? Oh, that was not what I wanted. Could you provide the definition in bullet points and in regular English? Okay. So I would like a very succinct checklist of things you would need to determine if the limit exists, or rather, in determining if the limit exists, period. My understanding is that you would first need to check if the limit itself can be substituted into the function, and that is defined, period. This would mean that we couldn't really evaluate infinity, but for finite numbers, this is reasonable. Period. And then additionally, we look from the left and right side, and if the limits are equal, then we have a resulting limit. Is that correct? Okay. Yep. So I guess it is to say that the limit is what the oh, okay. I think I don't need to do any more looking into this. So the limit would be what the function approaches as we get arbitrarily close to as we get arbitrarily close to the limit on our input. Maybe I could approach this from another way. Could you tell me what needs to be satisfied in order for a limit to exist? So, given this definition... Oh, no, that's correct. Okay. Okay, so yeah, so it looks like direct substitution is easiest, and then we check about the limits going from the left and right side. I'm not sure if we had that captured. Let's check. Can I just look at... Okay. We're just going to... Okay, yeah, actually I don't think I captured that. I think I captured... Okay, so we're going to get that. How do we determine if the limit exists within a function for calculus? Okay. Feel good about that. Oops. Okay. Perfect. So, let's check. We determine the left and right hand limits. Let's see. If direct substitution does not yield a finite value or is undefined, can we conclude that the limit doesn't exist? Or even in situations where the direct substitution is undefined, we can have a correct limit. Like if for left-hand and right-hand limits, instead of them being positive and negative infinity in the case described above, if they both approach positive infinity, if there was a case where this occurred. Maybe perhaps there was an absolute value operator in the denominator such that we only went to positive infinity. Would I have a limit in this case? Or do we only care about limits as they approach finite values in terms of asserting that a limit exists? Interesting. Okay. So it is the case that if direct substitution doesn't yield a finite or value or is undefined, I can't conclude that the limit doesn't exist. Okay. So we can't conclude that the limit's a finite number, but we could conclude that the limit is positive infinity. Okay. Okay. The formal definition of a limit requires the function to approach a finite value L. If the function's value grows without bound, then the limit in the standard sense does not exist. Okay. That is good to know. Okay. Okay. If the left hand and the right hand limits. Approach negative and positive infinity. If the result of taking the left, okay, if the result of taking the left and right hand limits results in positive and negative infinity for a given function. Does the limit of the function exist? Okay, so let's finish reading. Perfect. Okay. Oh, shoot. I don't know. Let's see. Yeah, that's fine. Okay. Sweet. Okay, so let's adjust this. The limit. The limit doesn't exist for the function. We first check direct substitution. Oh, wait a second. I actually think Gemini's wrong. Well, I don't know. Is it the case that for this function I could factor out the denominator such that I could resolve the limit? Oh, okay, yeah. Oh, you're right. I thought it was -1. If it were -1 on the numerator, and I could factor out the lower or the denominator, would I then have a limit? Or if I algebraically manipulate the function, that I remove the possibility of finding the limit, or it's not this equivalent function? I see. So even if we're in a situation where presently the form of the function does not allow us to find the limit, we could modify the function algebraically such that we could derive the limit. Okay, perfect. Okay, so the limit does not exist for the function. Direct substitution yields an undefined, is undefined. Undefined. The function can't be algebraically manipulated to yield a function where we would have a limit. Have a limit. We then check the limits of the function taken from the right and left hand side, given the end limit approaches positive infinity and the right hand limit of infinity. There is no limit for the function. The limit exists. Okay, next one. Okay, so that's kind of odd. So I guess the numerator has a lower power than the denominator, and so in cases where this is, we know that the limit is zero. Actually, I need to look up a negative exponent. Okay, so 2 to the negative 2 results in 0.25, so 1 over 4. Okay, so it's the equivalent of moving the number to the bottom, or like putting the number over 1 or under 1. And then, actually, well, I was pulling out paper. I think I'll just use Excalidraw. Okay, so in this case, it looks like 2 to the negative 2 is 1 over 4. And so I think for the negative ones, we can think them as this turning into this. And so in the situation we have ourselves in, we're looking at e to the x plus 1, e to the negative x. So I'm pretty sure that we're going to be, oh well, yeah, I'm almost entirely sure that we're going to be approaching 0, because this will grow incredibly fast, and then this will get actually smaller and smaller, like incredibly fast. So let's just write out our answer first, and then my only holdback is that I may have my intuition here may be incorrect. Let's actually double check. I think that's actually entirely correct. So we have 1 over 4, and then we have so instead of, so we'll substitute e for 2 just to make it more clear. And so this would be 2 to the 2 plus 1. And so that would evaluate 2, 1 over 4 over 5. And let's see, so that is the same thing as 1 over 4 divided by 5. So yeah, so I can just do 1 over 20, I believe. Okay, so that means we're just like approaching 0 at like Mach speed. So we are good there. Okay. Yep. Okay. Okay. For this one, this problem, the limit for this is 0 for this problem. The reason being is the exponent, the leading coefficient. No, yeah, the leading coefficient. Power is higher, degree is higher in the numerator, sorry, in the denominator than it is the numerator. Being this is the case, the numerator grows as x increases, the numerator grows more rapidly. Especially in the case, which causes the output of the function to get close to 0 as we approach infinity. Okay. Okay, now we'll give a little check, see if we are on the right track. I believe this one is correct. I'd say I'm like 90% confident. Well, I'd say I think I'm like a 95% confident. Okay, it would be important for me to actually get my answer. Do. Oh, okay. So my description about the leading coefficients degree is not correct, because, well, I don't know if I agree with that. Okay, so I guess this, well, it is true. Like this, I think this is correct. However, it's the case that they don't quite treat it as a polynomial, and they more treat it as an exponential. But my intuition about like the denominator approaching infinity, or sorry, the denominator increasing rapidly while the numerator approaches 0. Or sorry, yeah. Anyway, so okay, so I need to call these exponential terms rather than polynomial degrees. Oh yeah, of course, because it's a polynomial degree if I have if I have x to the something, right? Or x to the 5 or x to the 4, and then we can talk about leading coefficients. But if my x is exponential or is a power, then like it's obviously the case that yeah, it's obviously the case that it's going to grow incredibly rapidly. Okay, no, yeah, this is, so I was wrong. My I confused the polynomial versus exponential. And exponential meaning like specifically that we have our input variable is within the exponent. Okay, that's good. So being the exponent's degree, let's see, because okay, we problem so we get 1 over x over e to the x plus x, and then we could multiply that, so it'd be e what was that look like? Okay, e to the 2x. Okay, or sorry, e 2x plus ex. E 2x plus ex. Okay. Okay. Opa. What the heck? Am I in caps? Okay, yeah. One over e to the 2x plus e to the x. The denominator grows incredibly rapidly. exponential function. Because of this, the resulting value approaches 0. 0 as we approach infinity. Okay, next. Okay, so I think these are the ones where it'll become a little bit harder because I'm less familiar with the like trigonometry functions. So if we're taking the limit to infinity for this one, in the bottom here we do have sorry. In the bottom here, we don't have, or our degree is 1, or maybe like a exponential degree is 1, and then in the top we're 2 here. So the numerator is higher than the denominator, and so the numerator is going to like increase very rapidly compared to the denominator. So being that that's the case, I would say that this one let's see. So I think this has to do with our asymptote. I feel like we okay. I feel like I have a rule about the numerator being 1 degree higher than the denominator. For slanted asymptotes, perhaps? Or maybe that's when it's equal. Okay. I can't recall this. So this is actually one thing I'm like, like it's clearly the case now, but it's surprising that when finding the limit, I'm like really dialing into like finding asymptotes, and it like I said, it's obviously the case now that it's reasonable, but especially when we're taking the limit of infinity. When we take the limit of infinity, we are finding like asymptotes. But it's only the case if we have a horizontal asymptote, because an oblique asymptote would approach infinity as we approach it, as the input approaches infinity, and a vertical asymptote like as we approach infinity, like we don't have a vertical asymptote. I guess vertical asymptotes occur on like finite x values. Yes, I think I'm fair to say that. Okay, so being that this is the case, I don't think, given that we're taking the limit of infinity, that we'd have a limit, a finite limit. So I'm going to say the limit does not exist for this function. Because the leading coefficient of the numerator is higher than the leading coefficient of the oh shoot, no, this is correct, denominator. We would have like odd behavior, like there are points, or at least I'm assuming there are points for this x where we have an asymptote, and so if I were evaluating this function in terms of finding its vertical asymptotes, then I would have to look for cases where this gets arbitrarily close to 0. I can't recall what this I'm pretty sure for the sine function we're gonna have something repeating, right? But I can't recall which values we're repeating. Maybe 0 to 1, or 1 to yeah, I'm not sure. Anyway, so it is the case that we would need to be careful of that. But since we're taking the limit of infinity, and we have like a higher coefficient on the leading, we have a higher degree on the leading coefficient, then we know that the upper, like as we approach infinity, the output also approaches infinity. We can, as the input approaches infinity, the output okay. I'm wanting to know the range of values for the sine function. What is the range of values for the sine function? Okay, -1 to 1 on a closed loop. Perfect. Actually, I think I want to capture that. What is the range? Is this true for all the other trigonometric functions? Interesting. Oh, okay. This is actually quite interesting. Okay, I think it is quite important to pull this stuff into Anki. At least describing the range of values, because then this helps me to understand situations where we'll have infinities, or yeah, this will help me understand like especially for the secant or cosecant function, being that we can go to, you know, they can't approach infinity. That has an effect on like if they're in the anyway, I just have to keep that in mind. For sine functions, they're only going to be ever plus or minus 1, right? So they're not actually like a huge issue, but okay. This is important to know. And so trigonometric functions. So maybe next time we'll just go through these real quick. Trig functions. And then we'll go the most recent, and then I'm going to close this one out and get a new Gemini. I guess I could have just created a new chat, but it'd be like that. Okay, sweet. I feel confident about that. The limit taken the limit taken to infinity. Okay, I think I'm gonna be a little bold in my thing here, or my answer. And I'm going to say because the leading coefficient of the numerator is higher than we can be sure that the output. The only case, the cases in which we have finite. No, that's not true. Put another way, because this function is unbounded, and can be sure that if we take the limit of infinity, we will not approach a finite value. Okay, I feel pretty confident about it. This may be like an over assertion, but I feel pretty confident about it. Let's see if let's see what Gemini thinks. Find the limit if it exists. If it exists, explain why not. Okay. Is my answer correct? Doop. I'm on the right track. Oh, no. Okay. I do need to work on evaluating this more. Doop. Nope. I want to go like this. Okay, so I'm correct about the dominant terms here. Since I have the sine function and it oscillates between -1 and 1, even though that -2x grows infinitely large in the negative direction, sine of x will always be a bounded value. Okay, so I just need to be careful of that. Dividing by the dominant term. To analyze the limit as x approaches infinity, we can divide both of the numerator and the denominator by the highest power of x in the denominator, which is x. Okay, so this is new. Dominant term. Learn. Dividing by the dominant term. Approach for analyzing limits. Evaluating the list of limits of individual terms. my. Okay. So this we're using the squeeze theorem. But this is new to me, being able to pull that out like it's happening into three different functions. And then the overall limit. Yeah, that's a good question. Okay. And it looks like as we're going through, oh, sorry, this is simplification. Oh, okay. Okay. So, we're not doing all three of these. We're taking the limits of the individual terms. Because if we take the limits of individual terms, they, like by the limit laws, we can still do operations after them when we're determining like limits and stuff. Okay. Okay, so we got a squeeze theorem that helps us get the overall limit. So while my intuition was correct, it could have not been correct. So something like this, finding the overall limit, is like an important thing. Okay, so I think I'm going to stop on that one, and then we'll do this one real quick next time. And then we'll just continue down the test. I think today was quite productive. Yeah. Sweet. Okay. Yeah, I guess I'll be... Oh, actually, is this my last day of this week? Okay. It is. Now that I'm thinking about it, streaming on Friday does sound pretty attractive. Because I'm really excited to dive into statistics, and so I'd like to have calculus done. Okay, yeah, maybe we'll try Friday morning, banging out this test. I still would like to do this other test as well, when I feel confident in my abilities. To like test myself, because I should be pretty much getting all of these right if I've understood things correctly, right? Okay. Yeah, so I think okay. Yeah, okay. I think I am going to switch it up, and I'm going to do... I'll try to get through this test. Well, yeah, I'm not going to go past doing the part A. So maybe next week I'll work on completing this one during those 3 hours. Hopefully I'm able to do that. Yeah, I mean, this one's only 8 pages, so but I don't know, who knows. Okay, because I think both sum up to 80, so it's not like we just happen to take 2 more pages on the practice A. Okay, so yeah, so we'll go through the second one probably next week. So my hope is that I complete calculus by the end of next week. Yeah, I think that's my desire. Perfect. And then I would be able to start on statistics at on looks like the 12th, which would be fun. I'm like super hyped to start this statistics. So sweet. Well, I will see you guys tomorrow. Or sorry, see you guys on Monday. Or sorry, Friday.